So this presentation is about parametric modeling for the quantitative study of microclimate of historical urban setting, and will introduce a slightly different topic. Also, a brief introduction about myself, as I joined the group of Elena, bringing a complementary expertise in heritage science and environmental studies for conservation and climate-induced risk assessment. Also, the projects that I will be presenting today started before I joined the group, but then I could leverage the methodologies they implemented and optimized on other case studies which I'm currently working on. As an initial premise, in principle, all the intervention on the urban fabric must implement a multiscalar decision support approach, and this is even more crucial for built heritage. For conservation, but also for climate mitigation and adaptation purposes, the main urban design factors are the urban geometry, the building materials, and the natural elements, such as those sketched here, such as vegetation and water elements. Bioclimatic studies can integrate information gathered through on-site inspections and field surveys, and can also leverage computational fluid dynamics simulation to investigate the relationship between the local climate and the layout of the town, also to inform sustainable management strategies and renovation solutions. The first project, called PROSIT, developed and used an integrated design platform to assess and quantify sustainability in construction. The case study is the ex-Corradini complex, an evidence of an historical industrial facility built in the eastern district of Naples and dating back to the first decades of the 19th century. With the construction of the first Italian railway line, the Napoli Verticchio, a sequence of factories progressively developed in the area, along the coastline and the neighboring municipality of San Giovanni a Teduccio, which is an important industrial area. We started by analyzing the relationship of the complex with this neighborhood, highlighting its connection to the city center and the development potential of the district. In this schema are synthesized some strengths and weaknesses of the regeneration project for the area, which was drafted by the municipality in 2012. Among the main limitations that were found, there were environmental risks and the poor connections with the neighborhood. A GIS information database integrated into the BIM model was used for the urban analysis supporting the design process at an intermediate scale, closer to the building. The approach involved a semi-automatic process to import data from the existing WebGIS databases and the integration of real elements, such as buildings and streets, as parametric objects of the BIM model. This is an example of the information that can be found on existing open WebGIS, which could be manually integrated into the model depending on the scope of the analysis. As you can see, the GIS database also contains several information on the elevation of the urban fabric. Visual programming language, which also Christie's previously showed you, was used to develop a script allowing to automatically import OpenStreetMap data into Revit, transforming the textual geometric information into three-dimensional data, so to translate the GIS data into Revit parameters. Here is schematized the general workflow from OpenStreetMap database to the BIM model in Revit through the BPL plugins. The same workflow was implemented to two different codes. Here on top you can see the one written in Grasshopper inside Rhinoceros, and below Dynamo, which is installed as part of Revit, which was the one used by Christie's. As you can easily notice, actually one script is much simpler than the other, and we do prefer using the Grasshopper one. This is the outcome of the procedure, where data on, for example, building shapes and their functions were acquired and integrated inside Revit, where they could be graphically represented as shown in this example. Then the focus was deepened on the specific building under study, which you can see here integrated into the urban context with its full Revit model in white. A BIM model at the urban scale, even if with a coarse detail, is extremely useful to implement decision support through simulations. And here you can see an example of sunshine simulation that could be used to support the design of renewable energy solutions on the building and its outdoor spaces. As another example, here is shown the case in the winter season, where it was possible to highlight parts of the buildings that get less sunshine during the day. This simulation is slightly different, as it shows the amount of energy hitting the surfaces of the building throughout the whole year, so highlighting the best areas to use renewable energy systems. Finally, here is an example of a simulation approach based on computational fluid dynamics. So through CFD, it was possible to investigate a combination of more complex physical phenomena, such as here is depicted the intensity and direction of wind in summer on the left-hand side and winter on the right-hand side, also allowing to study the effect of water and vegetation elements on comfort. This type of analysis requires more computational effort and can be leveraged to get a picture of the effect of the seasonal conditions critical to further support the design of informed intervention. In this picture are brought together the results of all the simulative environmental analysis carried out during both the summer and the winter cases, which could be used to support the design of the intervention. We identified potential strengths to be exploited and problems to be solved. For example, here for the installation of photovoltaic panels, as well as the areas with improper shape duration. In this case, a specific project intervention was proposed for the redevelopment of the complex to favor a reconnection with the city, which was separated by the railway, but also including solutions for the environmental energy improvement of the building and the relevant open spaces, together with renewable energy solution, which were hypothesized as the installation of photovoltaic panels integrating on the rooftop of the buildings. Well, although simulation are great, architects are also love working on physical models, so here is a nice example of those. And finally, the HB model realized was gamified to allow the navigation of the areas, interactively exploring the sunlight entering the building during the day in different seasons through real-time rendering. Here is a taste of the game, which we also proposed to groups of kids last week in occasion of the European Research Night. The second project, TechStart, addressed comfort and energy efficiency in historical buildings, focusing on an environmental study of the passive potential of the so-called liminal spaces, so the transitional spaces of historical buildings. The case study is Palazzo Costabili, an historical building that houses the National Archaeological Museum of Ferrara and is located in the city center where different other urban typologies coexist. Together with a team of the University of Ferrara collaborating with us, it was possible to implement an on-site environmental monitoring of the building, and also thanks to the heterogeneity of the spaces occurring in the site, some of which are here represented, it was possible to study most of the similar transitional spaces in the city of Ferrara. Here is synthesized the workflow of the research, which, starting from a collection of documentary data and a geometrical surveys, developed an HP model of the building within its context. In parallel, the environmental monitoring data was acquired to be compared with the simulation results up to the study of the most effective design solutions based on the scalability of the project to the entire city. The geometrical surveys was carried out integrating photogrammetry and SLAM laser scanner, and the in situ survey, including the entire building plus its open spaces and courtyards, lasted less than 1 day. Then a point cloud was developed in the post-processing phase and positioned inside a WebGIS application, improving the procedure that was already implemented and used in PROSIT. Here is shown the editing phase of the WebGIS, which we checked and reviewed on site. And here is the VPL script that brought GIS data into Rhinoceros to obtain this three-dimensional model as a result. Then the point cloud was integrated into the model inside Rhinoceros through another VPL script. And simplified shapes are shown here, were extracted again inside Rhinoceros to obtain a computational fluid dynamics simulation model, which was finally run into the Ultimate software. This is the complex old code used for the export of the CFD model, and here is the result visualized within Ultimate. So notwithstanding the very rough graphical interface, thanks to this software, we were able to study the complicated physical interaction among the several factors which were relevant to the environmental analysis. Also, the meteorological data, which was monitored on site, was reshaped using a Python code, which is shown here, to be used as an input for the NVMET simulations, which were carried out using the full forcing mode, a method that considers local measured conditions to improve model accuracy and its representativeness of the real phenomena. Here are the results in terms of the surface temperatures of the building simulated by NVMET in the historical context, and here shown back in Rhinoceros interface for a nicer representation. Finally, this video summarizes the entire procedures from the beginning, so using the VPL script to obtain the three-dimensional model of the building within its context in the city, and finally to obtain the model ready to be run in NVMET. One last example is dedicated to an investigation which we are currently working on about the use of parametric modeling to support the quantitative study of microclimate of more complex historical urban setting. In this case, the study involves the methodological approach for the quantitative analysis of the microclimate of Chuandixia, which is a small city, small village near Beijing in China, which is also located at about 650 meters above sea level. In this case, the village has great historical and cultural values, as it was built during the Ming Dynasty, following traditional design principle of Feng Shui, which is an ancient body of knowledge that evolved from Chinese philosophy and embodies the Chinese ecological practices to harmonize people with the environment. The theory of the four emblems within Feng Shui, which is sketched here, is key to understanding the role of environmental design to identifying a promising place for the foundation of a city. So based on the observation of the landscape and the layout and orientation of the settlement, Chuandixia was built following the configuration of the territory, optimizing, for example, the sun path and summer breezes. The so-called Ming Tang here, the first nucleus of the settlement, was ideally chosen with very close to a river flow and surrounded by hills and protected by a rock formation called the Dragon Vein, which constitute a long chain starting from the pit of ancestors and ending to the hill of parents. The principle of Feng Shui could also be applied to traditional Chinese housing units as the single-story courtyards, which is shown here on the left-hand side. Here you can see the settlement that is very dense and built around the hillside with courtyard buildings arranged in a radial pattern to fit the surrounding terrain. And the core nucleus of the settlement is also separated from the rest of the buildings through a steep change of elevation between their respective ground levels. And in terms of archaeological technology, this planimetric approach is also advantageous in solving some building ventilation issues and also allowing for greater sunlight penetration into the dense clusters of the building. Again, the use of visual parametric language allowed us to exploit the parametric approach to support an accurate geometrical representation of this complex topography, and also the morphology typical of other historical village, integrated so inputs from various sources and promoting interoperability between the CAD and the CFD software. The script again used the Grasshopper tool, and in this case, even though it was possible to automatically process the terrain and vegetation within the script, we prefer to manually refine these passages directly inside MDNet. Here is shown the morphology of the village terrain, which was modeled using the lens design plugin inside Rhinoceros, through which it was possible to import the digital elevation model of the area directly from the Earth Explorer satellite database of the United States Geological Survey. The geometric configuration of the buildings in the settlement was modeled starting from the GIS maps, which were further checked and refined through the comparison with high-resolution satellite images and on-site pictures. Both the buildings and the dam were then georeferenced and put together into a single three-dimensional model of the area. And a custom Grasshopper component was created to leverage the Rhinoceros viewport interface to manually select the survey area and to adjust the orientation of the settlement with respect to north, while simultaneously updating the information exported to the CFD model every time the active viewport changes. The Gizmo plugin was used to define the latitude and longitude coordinates of the location, And then the Dragonfly Legacy plugin, part of the Ladybug collection of environmental design tools, was used to connect Rhinoceros to Antimet, developing the spatial input file needed to carry out the urban microclimate analysis. This is the entire workflow to obtain the model, which was also useful to consolidate the developed procedure and to promote correct implementation of the geometrical manipulation, information enrichment, and interoperability processes, also to be exploited for other case studies involving such complex geometries, such as those which are typical of the historical villages. Thanks to this procedure, it was possible to export the final file in the format ready to be executed in Envimet, which you can see here directly inside the software. And we also manually refined the digital elevation model, which was slightly interpolated in the US database system, to better represent the very steep separation between the upper center of the town and the rest of the village on this side. Still, in the Envimet environment, it was also manually integrated into the model, the distribution and representation of some selected detailed three-dimensional objects, such as the tree species surrounding the housing units, to better consider their effect in terms of shading and evotranspiration exchanges. Since in this case we had no availability of on-site monitoring data, we gathered the climatology of the area through high time and space resolution environmental data downloaded from the European Copernicus portal. And as you can see, the climate of Chuandixia resulted to be temperate monsoon with typical cold winters and cool summers, and with precipitation concentrated in the summer months. The prevailing winds come from the west-northwest direction in winter and south-southwest direction in summer. And thanks to this information, some initial simulations were run to analyze the comfort conditions in the village throughout the year, as well as quantitative analysis of the effect of the Feng Shui settlement principles. Here is shown just to wrap up all the presentation, a last example of speed and direction of the winds that could be simulated on a winter day in the village. And the results highlighted that the interaction between the morphology of the landscape and the layout density and orientation of the buildings were effective in slowing the intensity of the prevailing cold wind coming from west side in winter, so effectively dampening their intensity, and thanks to the configuration of the hills surrounding the village. So this was the last example, and I thank you.